the modern age, there are more other methods too, but I'll try to discuss really major ones. So approach 1 is distance supervision. So what does this mean? It's actually quite simple. The naming is a bit maybe not too intuitive, but the approach means that distance supervision means that you basically generate several candidates and you find out which arrive at the answers. So if you're able to generate a good number of candidates that's not too large, but still large enough to contain a one candidate that arrives at the answer, then you can basically use these candidates as the positive examples and the rest as the negative examples and try to do whatever you want. You can try to formulate this as a stick-to-stick problem, just like strong supervision, because you're considering these candidates that arrive at the answers as the positive, as the ground truths, although they might not be, of course, right? This has several advantages in that, of course, you don't have to worry too much about your model. What you have to worry more about is how you can have a good rule to generate these candidates. But in many cases, you might not be able to generate a small enough number of candidates. This will not be working too well if you're not able to arrive at the answer with your generated candidates because you will not have any possible example. Or if you have too many candidates, then maybe it also means, well, actually, if you have too many candidates, then it also means that you have too many negative examples. So you might have to sample some of them. So distance supervision is a popular approach, but it has to be taken with a grain of salt. And also, but still, I think it's very promising approach in many cases. But it really depends. It has a high dependency on how you generate the candidates. And this is also oftentimes through rules. So you define some rules given your knowledge about the target database or target logic space. It has a lot of inductive bias. Okay. And approach 2 is you can try to parse as a latent, you can try to consider the parse as a latent variable. So it's a bit more mathematical approach in that you're formulating this problem as a probabilistic model. And suppose that your target parse is Y. This is target parse. So SQL query basically in WikiSQL or the NL2 SQL example. So this is a SQL, and this is the query, input query, natural language query, right? So what you're trying to formulate or what you're trying to compute is this probability distribution, right? And how do you compute this? Well, as I said, if you try to compute this directly, or if you try to model this directly, it doesn't really make sense because Y is an answer and it doesn't directly depend on the natural language query. It actually has an intermediate form, which is parse, P, that leads to the answer by executing on the database. So that's why you basically formulate this as a summation of this probability distribution, which is now also you're trying to include the parse P into the probability. So hopefully you all agree with this first equality, because you're marginalizing, you're basically formulating P of y given x as the marginalization of P of y and P given x. So everyone agrees with that, hopefully. So it's a simple math. And then you formulate this as, you basically translate this into the multiplication of these two probability distributions, P of y given P and x, and P of P given x. And it's a simple Bayes rule that if you multiply these two, then it's P of y, P given x, right? So that's why it's equivalent. So looking into this equation more closely, really the important things again is how we can generate the candidate parses, right? So it actually doesn't really, it's not too much different from the distance supervision. The core difference is that in distance supervision, you're trying to create the data set in a more of a very synthetic or in a pseudo way. But in approach 2, instead of creating a data set in a pseudo way, which might not be mathematically rigorous, you're instead injecting that pseudoness of distance supervision into your probability distribution, so that mathematically you are very rigorous about how you approach this problem. So hopefully you understand what the relationship between approach 1 and 2. So 2 is good in that this is very mathematically exact. But you have the same problem though, because if there are too many possible candidates, the marginalizing the probability is intractable. So suppose that the number of possible candidates is like millions. Then what that means is then you have to actually consider the probability distribution for all these millions of candidates, which is very slow. So that's why what we do in practice is that we need to sample P. And when we are sampling P, it's actually, once we have trained the model, it's quite straightforward, because so I'll actually write this down the next page. So what was the equation? So again, P of y given x is summation of P of y given P and x. This is big P, by the way. There are two different P's. Hopefully you don't get confused. This is a probability. This piece, the small piece parse. P of P, small p given x, right? And small p. And you know that because this is basically, what is this equivalent to? This is basically the expectation over P. Actually, I'll write of P of y given P given P and x, right? Because that's the definition of expectation of certain value. Hopefully remember that. Recall this is equivalent to expectation of certain function over A is equivalent to summation of FA times P of A over all A, right? So everyone knows this, I hope so. So this is just recall. So then Now, what you can think of this is then, because this is expectation, when you're during your inference, you can sample P, and then you basically just sum those values by just you sample P, and then you can just use these values. I'm saying that sample P, so you have a lot of candidates, and then you sample P, and then you compute the probability for these P, and then just compute the summation on those values. That's exactly what the expectation is enabling you to do, right? So during inference time, it's easy to approximate this expectation without any bias, right? This is just basically not equality, but what I'm saying is this is approximately equal to, without any bias, you sample P so you sample P, and then you just basically do the summation, right? So probably it's not the best way to write. So just a second. So what I was trying to say is you sample P, yep. So basically you sample P and just basically just consider your samples as your entire distribution, and then you will not have any bias. So that's really the good thing about this formulation, because you're making this as an expectation of this P of y given P and x. But there's one problem with this, which is that, okay, it's great. It's great that this inference can be approximated without any bias. But can you say that, can you approximate the gradients too during training? And it turns out that you cannot just approximate in the same way. So I'll not go into details today, because hopefully you'll be able to get to this in the reinforcement learning class, or maybe advanced deep learning class. But the point is that what I wanted to say is that during inference time, it's straightforward to actually compute the P of y given P and x. But in the training time, when you're trying to compute the gradients of P, because that's what you're really trying to obtain, right? Then in that case, then you actually have to do some math. And that's exactly what reinforce is doing. In a nutshell, what reinforce does for you is it enables you to approximate the gradient in an unbiased way. We just saw how we can do this for the inference in an unbiased way, which is straightforward. But for computing gradients, it's not straightforward. You have to do some tricks, and that's what reinforce does for you. So that's how you compute gradients without any bias. And that's called also policy gradient. And also that's really popular mechanism in reinforcement learning. But this has no bias, but high variance. And what does high variance means in general? It's really hard to train, because it has so much, I would say, fluctuation, that it's really hard to get to good optimization destination. So in practice, actually, I think I mentioned this a few more times in previous lectures. No bias is a very important thing in theory, but in practice, actually many people prefer biased estimation. And I think I mentioned that one example was sick to sick, teacher forcing, right? Teacher forcing is actually biased. It's not unbiased estimation. But because it has lower variance than the unbiased high variance estimation, it actually leads to pretty good, I would say, optima than the unbiased but high variance estimation. So you can, and I think I mentioned that in previous lectures, that if you want to do sig-to-sig in no bias way, then something like policy gradient is required. But in practice, no one really uses it unless they're kind of fine-tuning at the end. In some papers, they try to do this. They try to fine-tune at the end after biased, a lot of iterations with biased loss, and then they basically, at the end, they try to fine-tune with unbiased high variance basically estimation. And there are several reinforcement learning techniques such as actor-critic, and these are actually biased estimations too. So you'll see that, okay, these are biased, but they have they have lower variance that in practice they lead to better optima again. So the concept is quite important, that what's the difference between bias and variance, and why you need relatively low bias, but also in many cases, having some bias is not a problem relative to having super high variance. Okay. So we basically cover a few more tasks, right? Syntactic here and semantic. And we saw that how we formulate these tasks, how we approach these problems is sometimes quite similar to how we did with other tasks. Semantic parsing is quite similar to text generation if you're using sig-to-sig. If you're using the latent variable techniques, then for the weak supervision, it's a bit different, but still you're dealing with some sig-to-sig component in the model. Syntactic parsing, I think it's a bit different from all these three if you're talking about the traditional constituency parsing, but modern methods such as transition-based dependence parsing is also quite similar to sig-to-sig or text generation. So I mentioned that up to this is kind of half of the class, and the rest of the class will be covering these two, pre-training, fine-tuning, and probably will be mostly focusing on the pre-training and fine-tuning, and a bit on the in-context learning, because this is really super new that it's not really, we do not understand this very well at the moment. It's very recent. But at least it's good to know what's happening in the literature for many of you. So for the rest of the class, I'll be going through a few papers, and we'll be really talking about how we can interpret and also write a scientific paper. And there's actually a class in KAIST, how to write a scientific paper. I think many of you have already taken it or are taking it right now, and I highly recommend it. But I'm dedicating today's portion of today's class and also next class and also an assignment on this too, because number one, it is very important if you want to write a paper, and number two, even if you have taken or are taking this scientific paper class, NLP and ML papers have slightly different tastes than, for instance, biology, physics papers. So I think it's a bit, it's worth it to really dedicate one or two classes, because being knowledgeable of these and leveraging these knowledge will enable you to write a paper much more effectively and efficiently. And I always say this, it's like a small investment now. It might be a bit boring, but that will save your time a lot during your course of study. And of course, if you're staying in the academia or research, then it will be very useful for the rest of your career too, right? So we're going to have a short break until 3:20, and we'll devote the rest 30 minutes on the analysis. And it will be important for you because you'll use these techniques in your discussion next lecture on Wednesday. So see you in 3 minutes at 3:20. Hi, everyone. Welcome back. Okay, so let's go into the paper analysis. So I'll first give you a very rough breakdowns of what kind of papers there are. Of course, these are subjective and not comprehensive, but in my experience, you can fit in most papers, fit most papers into one of these categories. So let me first briefly describe this. And I think you're encouraged to use this breakdown in your discussion on Wednesday and try to see if if the paper fits into one of these categories, or maybe it doesn't fit into one of them, that you can try to propose a new category or subcategory. So I usually think of a paper in largely one of three categories: task, method, or analysis. So what is task paper or dataset paper? So they propose a new task and or dataset. So um, in the first case, 1A, it could propose an entirely new task. So for instance, I would say someone probably proposed uh, every task for the first time on some day, right? So for instance, machine translation was formally proposed many years ago, like 1960s, 50s. But relatively maybe recent tasks are, for instance, I would say um, like fact verification. Of course, this is more recent because it's a bit more complicated than, or maybe more, it has more components, I think, than other tasks. So the paper could be proposing an entirely new task. Or B, 1B, the paper could be proposing a new data set for an existing task. So for many papers, many dataset papers fall into this subcategory. For instance, question answering has existed for many years, but you can propose a new data set on question answering, and that could be 1B. And I want to also mention that it cannot be always clearly distinguished even between 1A and 1B, because a data set can some data set, if they're sufficiently different from other data sets in the same task, then maybe you can consider that data set as a new task. So it's not always clear if the proposed data set should be considered as a new task or existing task. But I think it's more of subjective, and it's not super discrete line between them. It's more of a gray area. But it's easier to understand what this means through examples than, I think, trying to describe everything on this slide. And also 1C is you're sometimes proposing a new evaluation metric for an existing data set and task. So for question answering or machine reading comprehension, for instance, most popular evaluation metric is F1 and exact match. But you might want to propose a new evaluation metric because existing evaluation metrics are not good enough. And of course, you will have to persuade readers why your evaluation metric is also much better, and also the difference is significant enough for the publication. And number two, method paper. So in this case, you're proposing a new method for a target task. What that means is you're either achieving the best performance in one or more evaluation metrics. Some things like accuracy, speed, memory complexity, etc., without altering the task. So your task is the same, so you can exactly compare with previous papers on these tasks. You basically just achieved better numbers than them. So 2A, I think, is one of the most straightforward way to write a paper, because I'm not saying it's like the only way or the best way to write a paper, but it's quite straightforward because at least everyone agrees what this means, why this is important. If they agree that task is significant enough, because if task is significant enough, then getting the best number in the task is definitely then meaningful, right? 2B is you're imposing an additional restriction on the task and show the best performance. For instance, in zero shot or few shot, you're saying that you don't have many training examples, even though dataset was not originally meant for that. So maybe you're considering squad as your dataset, but instead of considering all those 80,000 training examples, maybe you want to show that even with just training on the 1,000 examples in the data, you can achieve very good performance compared to other methods that only used 1,000 examples. And of course, your performance might not be better than or comparable to the models that used entire data set. So you cannot really say that it has achieved the best performance without altering the task. But instead, you altered some aspects in the task so that you can have a new perspective on the task. Zero shot is one case. Continual learning is another case that in this case, you're considering you're learning one task at a time on the same model. And you're saying that when you're learning a second task, in many cases, you forget what your first task, you forget about the first task. So in this case, you are evaluating on the first task after training on the second task, and you want to get better number than the vanilla way. And of course, again here, your number will not be as good as just training the model on the first task, but you have imposed this setup, which is first, of course, has to be proven to the readers, or it has to persuade the reader first why that imposing the restriction is meaningful or it's realistic, which means does it happen in the real life scenarios? And if that's the case, then it makes sense that you actually impose this restriction. And 2C is you're proposing a new paradigm for approaching an existing problem. And in this case, you might not be imposing an additional restriction, and you might not be achieving the best performance, but how you approach the problem is quite different and also seems promising enough that you persuade the readers that this is a new paradigm, that the future work will be on someday using this paradigm. And maybe now it's not as good as other works, but it has a good benefits that it's worth mentioning. So these are usually, if they actually succeed, then really big papers. For instance, early neural network papers are kind of fall into this category. They were not actually maybe showing better performance than SVMs in the early days, but still they were trying to propose a new paradigm, and they were saying this might actually at some point really change the field. 3 is analysis paper. In this category, you analyzes existing tasks or methods. So what kind of analysis you want to do? Maybe you want to refute a popularly held belief about a task or method, theoretically or experimentally. 3B is you verifies an experimentally proven belief with theories or vice versa. Or 3C is that you reveal some interesting characteristics about a task or method. And I want to mention that papers don't always fall into one category or subcategories. They oftentimes actually fall into several different categories and subcategories. So don't think of it as a super exclusive thing. And we'll see this soon, how this works. And what's the role of each? And then when we're trying to analyze paper in more depth, we'll try to classify the role of each sentence in abstract and intro. So I think they can be largely broken down into a few roles. These are not comprehensive again. There might be more, but I think these are really often observed, and it's important to really um, be aware of these, because when you're writing a paper, you probably want to utilize most of these to make your paper very persuasive. So a sentence might be a background where you're giving a smooth introductory sentence before diving into the problem or your point. It might be a motivation where you're trying to motivate the readers what's problematic. It might be a proposal that describes what's being proposed in the paper. It might be a comparison to a previous work or many previous works. And here you're making a direct comparison very rigorously. You're making a maybe evaluation. You're actually talking about how your method is being evaluated, or you might be talking about some experimental results that your paper contains, and you might be also talking about the implications of these results, and they basically signify what they mean in general and in a grand scheme of things. And lastly, but of course not really lastly, there might be more of a related work that describes other works that are more loosely related than comparisons, I would say. So let's try to use these two tools, right? One is classifying each paper into one of these categories. And number two is classifying each sentence in the abstract into one of these categories for the following papers. And this will be exactly what you're going to be doing yourself with other students on Wednesday. So please pay attention. So here there are three papers that you should be already familiar. This one, and this one. These were in your reading list. And these are new ones that I haven't discussed before, but you will also be very familiar with these because they are talking about question answering too. So let's take a look then. So the first paper that we're going to look into is Treadall 2014. This is the first SIG-to-SIG paper that we discussed in the machine translation. And this can be considered as method paper. Why? Because it's not task paper because it doesn't propose a new data set. It actually utilizes existing machine translation data set called WMT. It's not really an analysis paper, I think, because it's not really trying to analyze the existing model. It's more of a method paper. And which category does this fall into then? So first of all, I'll go into this paper in case you don't remember this paper. So this paper was about this thing, right? Hopefully remember. This is the original SIG-to-SIG paper with encoder and decoder. And let's try to read the abstract first to actually try to categorize this paper into one of those paper categories. And we can also, of course, try to categorize each sentence too. But let's first read the paper. It says, in this paper, we propose a novel neural network model called RNN encoder-decoder that consists of two recurrent neural networks. One RNN encodes a sequence of symbols into fixed length vector representation, and the other decodes the representation into another sequence of symbols. The encoder and decoder of the proposed model are jointly trained to maximize the conditional probability of a target sequence given a source sequence. The performance of a statistical machine translation system is empirically found to improve by using the conditional probabilities of phrase pairs computed by the RNN encoder-decoder as an additional feature in the existing log linear model. Qualitatively, we show that the proposed model learns a semantically and syntactically meaningful representation of linguistic phrases. So it's an actually interesting paper because this paper was not really focused on getting the getting the state of the art performance in the WMT, because it was not able to actually back then. So if you look into the results here, they do not really compare against the SMT, which is statistical machine translation. They only compare against more of I would say RNNs and other neural network based papers, and also some, I would say, relatively easy, relatively, I would say, low performance SMT papers, right? So we cannot. So let's go back to the categories. So we cannot probably say that this falls into. So we know that this is a method paper, and we cannot probably say it achieved the best performance. We can say kind of it falls into B and C because it's kind of imposing an additional restriction that you're mainly comparing against neural network papers, right? Neural network models. But also, it's kind of proposing a new paradigm in a sense that it doesn't contain any rule-based components. It's entirely data-driven. It's fully neural network based. So if readers actually are persuaded that neural networks are really, I would say, very promising in the future, then they can be persuaded that also this paper has really meaningful contribution, because it will be opening a new door to the neural network based approaches for neural machine translation and machine translations, right? So personally, I think, and people might have different opinions, I think this falls into B and C. They kind of impose a restriction, and also it's kind of proposing a new paradigm for machine translation. And let's try to now classify each sentence into its role. I'll just go through the abstract because we don't have much time. So how about the first sentence? In this paper, we propose novel neural network. So clearly, this is about the proposal, right? They're talking about what they are talking about what they're proposing, and this is also about their proposal describing their method in more details. One RNN encoder encodes a sequence of symbols. And then they also describe in the third sentence their proposal too, right? And now we go into the performance of a statistical machine translation system is found to improve by using the conditional probabilities of phrase pairs computed by the RNN encoder decoder as an additional feature. So this is exactly what the paper is actually really arguing, right? So that it's basically the empirical experimental results, what the paper is saying. And also it again has a sentence that shows that describes about the experimental results too. Qualitatively, we show that the proposed model learns semantically and syntactically meaningful representations. This can be considered as, I think, empirical results, but also implications. So I'll say this is maybe implication. This is E, experiments. This is more of a proposals, and proposals, right? So we just saw that in the abstract, we have 3 proposal sentences and 1 experimental result sentence, and 1 implication sentence. So that was one quick way to really analyze how the paper is structured. Okay, so let's go into the second paper, which is Herman et al. 2015. So I say this is task and method paper because it actually propose a task and also method. So we'll actually see how that goes in the abstract. So let's read the abstract. Teaching machines to read natural language documents remains an elusive challenge. Machine reading systems can be tested on their ability to answer questions posed on the contents of documents that they have seen, but until now, large-scale training and test data sets have been missing for this type of evaluation. In this work, we define a new methodology that resolves this bottleneck and provides large-scale supervised reading comprehension data. This allows us to develop a class of attention-based deep neural networks that learns to read real documents and answer complex questions with minimal prior knowledge of language structure. All right, so it's clear that they actually propose data and also deep neural network model. So that's why this is a task paper and also model paper. And you can see a lot of papers actually approach this way. They try to propose a new task and also new model, new method, which makes sense because when you want to do a new problem, then you have to first actually define the problem, and also you will also talk about how your model differs and how you approach the problem, especially compared to relatively very obvious ways. So this is why I can think of this as a task plus method paper. And how about each sentence in abstract? So the first sentence, teaching machines to read natural language, blah, blah, to elusive challenge. So this is exactly background, right? If you're talking about some very general statement of background. And then or motivation. So maybe they are not super distinct from each other. Machine reading systems can be tested on their ability to answer questions posed on the contents of documents that they have seen. But, so when you see but, then it usually you're trying to motivate something by saying something is problematic. So at least second sentence is clearly a motivation. So this is, you're starting with some background and you're going into some motivation, right? And then you say in this work, we define a new methodology that resolve this bottleneck and provide large-scale data. So this is clearly proposal, and then you're describing further about proposal, but you can also think of this as also kind of implications. But I think it makes more sense to classify this into proposal. So in this case, you have background, motivation, and two proposal sentences. Good. All right. But we can do similar things on the introduction too. How about the third paper, Chen et al.? So you haven't read this paper previously. I mean, we haven't discussed this paper in this class, but let's take a look. So the title reads, A Thorough Examination of the CNN Daily Mail Reading Comprehension Task. It says, enabling a computer to understand a document so that it can answer comprehension question is a central yet unsolved goal of NLP. This is background, right? A key factor impeding its solution by machine learned systems is the limited availability of human annotated data. This is also kind of background, right? Ehrman et al., which we just read, right, seek to solve this problem by creating over 1 million training examples by pairing CNN and Daily Mail news articles with their summarized bullet points, and show that a neural network can then be trained to give good performance on this task. This is also kind of background. In this paper, we conduct a thorough examination of this new reading comprehension task. So this is what they're kind of doing. So it's kind of proposal, right? And our primary aim is to understand what depth of language understanding is required to do well on this task. They're talking about what they're doing too. We approach this from one side by doing a careful hand analysis of a small subset of the problems, and from the other by showing the simple, carefully designed systems can obtain accuracies of 73.6 and 76.6% on these two data sets, exceeding current state-of-the-art results by 7 to 10%, and approaching what we believe is the ceiling for performance of this task. So it's a bit long sentence. So it kind of starts with some proposal, and then it talks about some experimental results, right? And here, the last sentence is more of implications, right? What this means, what these results mean. It's kind of implication. So it's one sentence that has proposal and what that results in, and also implications. And now you see that why this is analysis paper and also kind of a model method paper, because they actually analyze this data set in a really very very closely. But they also actually propose a model, a simple model that can do pretty well. So it's kind of, I would say, method plus analysis. So let's go into next paper. I have only 4 minutes, so I'll be a bit quick. So this is the original squad paper. So let's read the abstract. We present the Stanford question answering dataset, a new reading comprehension dataset consisting of 100,000 questions posed by crowd workers on a set of Wikipedia articles, where the answer to each question is a segment of text from the corresponding reading passage. It's proposal, right? And we analyze the dataset to understand the types of reasoning required to answer the question, leaning heavily on dependency and constituency trees. So this is also kind of proposal what they're doing in the paper. We build a strong logistic regression model which achieves an F1 score of 51%, significant improvements over a simple baseline. It's kind of proposal plus experimental results, right? However, human performance is much higher, indicating that the data set presents a good challenge problem for future research. This is kind of implication, right? So that's like one way to really analyze the paper. So they basically, actually, they also have a model here too, but I think I don't really say this is a model paper, method paper, because it really focused on task and the method is very baseline. So that's why I'm saying it's subjective. Some people might say this is like plus method, but I think it's not really method. Let's go into last paper before we end our lecture today. So this is the popular paper, Transformer. So let's read the abstract again. Dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. So this is background, right? The best performing models also connect the encoder and decoder through an attention mechanism. Also background. We propose a new simple network architecture that so actually the previous sentence can be either B or motivation. They're kind of, it also kind of motivates why we want to use attention. We propose a simple network architecture, the transformer, based solely on attention mechanism, dispensing with recurrence and convolutions entirely. It's clearly proposals, right? Experiments on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. It's experiments, right? Our model achieved 28.4, blue on the WMT, and German translation task, improving over the existing best results, including ensemble by over 2 blue score. It's also experiments. On the WMT 2014, our model established a new single model, state-of-the-art, blah, 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 to 8 GPUs. Also experiments. We show that transformer generalized well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. This is also kind of experiments too. So, of course, how I divide these, each sentence is not, I would say, there is like, I'm not saying there's only one way to do that. You might also want to come up with your own categorization, but hopefully you get the point what I'm trying to say. And you see that when you have really strong results, abstract is relatively talking about a lot about the experiments, right? Because you want to emphasize your experiments, but then sometimes you talk a lot about the proposal when you're trying to you know also emphasize how your method is very novel and very different from the previous methods. So you see, like it's very. I mean, even if these 5 papers are all talking about NLP and kind of, in some sense, relatively similar things, how they structure the abstract is quite different, right? So, but then one thing I wanted to say before today's lecture is actually I have to actually go through this. I'm a bit over the. I don't have much time.